Alright. Okay, that's the plan. We need to get pipe flow done, and we need to do it before the tutorial next week. We cannot have our tutorials going faster than the lectures. Might make no much sense to you. So we need to get most of the pipe flow done today, maybe a bit next week, in the week after the break, and then after that next week's tutorial is on pipe flow. Okay, so I already hinted a little bit, but so we'll start with the energy equation. All right, I'll put it up in the one that you'll use, so no point beating around the bush and put up partial one. We'll do the whole thing. Then today we'll try to get through laminar and turbulent pipe flow. All right. Next week, the week after the break, Monday, maybe minor losses, and Tuesday piping network, and then I think pumps and all that. That follows nicely there. Okay. So okay, if this was a control volume, it looks like a pipe, but maybe it is, maybe it isn't, never mind. All right. So we have green. Okay. All right. Let's look at it in terms. My story a bit different than the notes are. I got different style. All right. So if you want to follow the style in the lecture notes, that's okay. If you want to follow the style in the textbook, also okay. Hopefully the story comes to the same. All right. So if you look at terms of so my style, energy. Why so thin? Okay. You got potential energy, isn't it? mgh. Why color wrong? All right. Okay. You got kinetic energy, mv squared. Okay, not? What other thing you got? Okay, so this part goes in, this part comes out. So also you got mgh, you got half mv squared. All right. There's this thing where I talked about, like Tai Chi one, you push. All right. So for this is the control volume. The control volume is at some pressure. All right. For for anything to go in, it needs to push into the control volume. All right. Now, although the pressure could be the same, never mind. But we are looking at the control volume for a piece of fluid of mass m to push in. All right. You need to push. The push is force times distance. All right. Now, pressure times area is the force times distance. This is This is to push the parcel into the control volume. Okay, no? That's why I need energy to push it in. And when it come out, the control volume will push it out. The pressure from inside the control volume will push the parcel of fluid out. So it's PAB. I talked about it earlier already, isn't it? Remember? Alright, area times the distance is actually a volume, isn't it? Pressure times volume. Alright? Equals pressure times volume. Alright, so we got those three energy going in. Okay? So we could have losses inside. Alright? Okay? Normally these losses, alright, is maybe the fluid shearing. Alright, the fluid shearing, you lose kinetic energy, or turbulence, you lose kinetic energy. That kinetic energy eventually starts to heat up to warm up the fluid. Okay? So, energy losses. The energy losses normally due to, in this, it could be a lot, but in this unit, we talk about the major losses, which is due to the pipe, all right, piping system, and minor losses, which is due to fittings, accessories. Okay, what I mean there is like valves, vents, contraction, expansion, T-joints, all those type of things. All right, all the piping accessories. Okay. What else are there? Okay, anything there? All right. You could also have turbine. Okay, if you have a turbine there, you can get some mechanical work out. All right. So work out lives in three ways. Okay, work in normally is a pump. Work in. Are we in work or energy? Energy in. Energy into the system. Okay, so that's about more or less what we just need to digest that a little bit, but that's the main concept. All right, energy going in, so energy can go in by being transported by the fluid. All right, here we don't worry about internal energy, enthalpy, and all that because our energy is relatively small. All right, if you have big changes in temperature and so on, then you need to worry about enthalpy and internal energy and so forth. Temperature change. Here we don't. So we have flow, we have potential energy, we have kinetic energy, we have flow energy. All right, energy to push the liquid into the control volume, and energy that pushes the liquid back out of the control volume. And it carries potential, kinetic. All right, we have turbine, we have losses that take energy out without taking any fluid out, and we have pump that put energy in. Okay. All right. Okay. So volume, can I say volume is this one is actually pressure times mass divided by rho, isn't it? Rho times volume is mass. Okay. All right. You okay so far? So this is you okay with flow energy, huh? All right. Although we arbitrarily draw the control volume, all right, but now we get control volume as such. If any liquid enters, it enters with some energy, stored energy. That stored energy is in its own pressure, right? The fluid like the spring is storing that pressure, right? That's stored there as well. Then call it pressure energy, call it flow energy, and everything. All right. So it's like potential, potential energy there. All right, like a spring, the pressure, the liquid or gas or whatever under pressure. Okay. So in steady state, okay, normally all our problems are steady state for now. All right, for steady state operation, E in equals to E out. All right, the energy going in will equal the energy coming out. Later I'll convert that to power. All right, energy per unit time. But now I'll just worry about energy. So energy is half mgh. Okay. Now let's write P over rho, P times mass over rho. All right. Plus kinetic half mv squared plus mg, no 2 here, mgh coming in plus E in, normally due to pump, all right, is equal to mv squared is equal to Pm over rho plus half mv squared plus mgh out plus E out due to what? Losses all right, plus E out due to turbine. Okay, if there's a little turbine wheel, the fluid turns the little turbine and generates shaft work out. Okay, that happens in hydroelectric power plants a lot. Also could happen in windmills and so on. You okay so far? So if I turn it into power, good. All right. Convert to power. So let's say flow in steady state. So the pressure, velocity, and the head coming in doesn't change. It's coming in at that, going out at that, everything. So if I were to take the time derivative of this, all right, is that it will just be look like this: m dot over rho plus half m dot g squared plus m dot gh in plus p power in due to pump. All right, no, the p no good, huh? Then you put e dot. All right, plus same old lah. Okay, maybe speed things up a bit. Okay, m dot dot. Okay, no. So that was all power. Energy is in joules, power in watts. All right, joules per second is watts. So if that's what happens. If that happens in 1 second, everything turns to power. Okay, now. All right. So power, flow power, flow kinetic power, potential power. All right. Pump power. This one, that one. Okay. Next step. I divide each term with m dot g. All right. I just like lah. Okay. You can do it like that also can, but like that very cumbersome. All right. It's like all the equation actually the same. All the energy equation in different forms actually the same one. You just divide or what. So I divide by m dot g. Huh? So what I have here, m dot g. So I get p over rho g plus v squared over 2g plus h in plus e dot in comma pump over m dot g is equal to p over rho g plus v squared over 2g plus h out plus e dot turbine okay or not? Alright, so I divide by m dot g. Okay? So it's still the same. This term represents the flow power, kinetic power, potential power, pump power, divided by m dot g, and so on and so forth. Is that okay so far? Alright. Now this is in, what's the units of this equation? Huh? What's the unit of every term? Every term must have the same unit, isn't it? Alright? 5 cats plus 5 dogs cannot jive. So what's the units? Well, you can try to work out this one or this one. Oh, this one's not obvious. Alright? So the units? Alright, it's a head. Alright, it's a unit of length. Okay? So although it's a unit of length, but a measure of either energy and power. Okay, so it measures, each of them has a unit of length, but it's actually a measure of power or energy. Alright, depends which way you go lah. Either go one up is energy, go one all the way up is power. Sorry, go one up is power, go two up is energy. Okay, so units of length, and we call that head. I think you heard that head floating around earlier, isn't it? Head, right? H, subscript, small h. Alright. So this part here is fine, we don't need to touch. But all this E dot over mg, you don't have to carry E dot over m dot g and all that, you don't like to carry like that all the way now. But if you want to convert the head to power, you multiply with m dot g. Okay? So I write here. Alright? So, to simplify things, I copy this. Okay? So, I don't like to write like this. So, this one become H pump. This one become head loss. This one become head turbine. But you want to convert back? Alright, I write here, in case you forget. Head pump is what? No, normally you don't want to convert like that. You want to convert like that. E pump. So the power, this one in watts or kilowatts, right, is equal to m dot g head pump. Okay? Right or not? Head is actually equal to E dot over m dot g. So if E dot is m dot g multiplied by head. Is that okay? So head is a measure of power. Right? You copy finish. Right? Head is a measure of power. Okay? And you want to convert from head to the power. Alright? You just multiply m dot g. So the rest are easy lah. E loss is equal to m dot g head loss. E dot turbine, m dot g turbine. M dot g h. Okay? So head is equal to m dot g. If you want to convert between the two, well, this is equal to this, or this is equal to m dot g times h. Any questions so far? So this is the equation that we'll use for pump problems or for piping problems again and again. Most of the time in this unit, no turbine. We don't actually cover turbine, we cover more pumps. And it could be a potential that we pumps. Rarely there is a turbine, but it can be there. There will definitely be losses. Alright. Okay, H pump and H turbine is as it is. Alright. There's not much to say about that. When we talk about the pumps, we'll worry about the head pump. This is like the head rise across the pump. Right? The energy the pump puts in is there in the H pump. Okay? Losses, we define like this. Okay? Head loss is equal to F L on D V squared on 2G plus sum of KL V squared on 2G. Alright? It's just defined like this. Alright? This is the definition of F and this is the definition of KL. Alright? This is due to major losses and this is due to minor losses. You ask why, there's no reason why. You can choose, we can actually do it differently, but this is the standard way. Alright? This is the standard. Alright? You can do other way, but you have to come and explain how your other way works. When you come and view your exam script and you fail doing other way. Then if I understand that you do other way and it's correct, then I can make the amendments. Alright? This is the standard way. All right. Okay. So this is due to major, and this is due to minor. Minor, I told you all the accessories. We won't talk about minor today. We just talk about the major one. All right. Minor losses, the accessories are all the elbows, valves, all the things. All right. The rotor meter. Okay. Anything like that is in the path of the flow. All right. So what they are, okay. This is the way it's defined. The KL is just the look. If you look at it, is the number of units of kinetic energy loss when your flow goes through an accessory. Right? So in other words, if your flow going through the accessory, maybe that be a valve or pipe or whatever, valve or elbow, what, and it loses 1 unit of kinetic energy, 1 times V squared on 2V, then the KL will be 1. If it loses 2 units of kinetic energy, the KL will be 2. If it uses 0.5 unit of kinetic energy, then it will be 0.5. Alright? This V is the velocity in the pipe. It could be different than the velocity coming in and the velocity going out. It could be different. Alright? V is velocity in pipe. Because depending on your system, the in might have a tank, the out might have another tank, the both velocity is 0, but the velocity in the pipe is not 0. Okay? So the V in and V out and V in the pipe could be different numbers. Could be the same number, could be different numbers. It depends. Alright? So that V is the velocity in the pipe. So the number of kinetic energy loss in the pipe relative to the flow is that here. Okay so far? That's the definition. Cannot ask why one. It's like that. Somebody choose like that. Alright? You can, again, I say you want to choose other way and redo the whole system. I don't like meters, I want my own job, whatever thing you need, also can. Just that you be out there alone. Alright? Oh no. Okay? Here, okay, number of units of kinetic energy loss due to pipe friction, due to when the flow goes through the pipe, which we'll study soon. Alright, why that happens. Alright? So F is the number of units of kinetic energy loss per unit distance of pipe. 1 unit of pipe is 1 diameter. The pipe characteristic is 1 diameter. So in 1 diameter length of pipe, the pipe diameter like this, so 1 diameter of pipe, 1 diameter length, the number of units of kinetic energy loss. So again, if F equals to 1, means in 1 diameter length of pipe is diameter, length is therefore the diameter there, you lose 1 unit kinetic energy. Normally you never get that high. Alright? Normally 0.02 or 0.01, something like that. Alright? Units of kinetic energy loss per unit length of pipe. Okay? Alright? So that's F. So the only thing now we have to do is to worry about F and KL. Then we've got that head loss sorted out. Okay or not? Alright? So F is the big unknown. Alright. And KL not so difficult lah. Mostly we get that number from charts, from experimental data and all that. Alright, F. Now F depend on whether the flow laminar, the flow turbulent. Alright. We have to talk about both today, laminar, turbulent, and so on. Then we worry about F. Okay? Okay, any questions so far? Okay, that's the energy equation. Alright, that's the one you use. If you want to convert from the energy equation back to actual energy or actual power, that's the equation you use out there, m dot GH. Remember? No half, huh? Okay, m dot GH, convert that. Right? Here. Okay. So So now let's consider a straight length of pipe. Again, this is for laminar lah. Alright. Let's consider a straight length of pipe. We apply this equation here in, here going in, here coming out. Alright. So for a straight length of pipe, alright, deep inside the pipe, not near the, we'll talk about entry length, entry later. Okay. But let me talk about deep inside first. Then I talk about inside first, that makes sense. Then later I talk about the entry. Alright. So very far away from the entry, it should have already reached its steady state. Correct or not? Right? So steady state means the velocity profile doesn't change anymore. Steady state. Alright? Deep, far away from any elbow, any bend, any entry or any problem like that, far away it will reach its steady state. Okay? Its steady state is at the wall of the pipe, the velocity must be 0. Alright? Obviously the velocity can be 0 everywhere and not nothing. So in the center the velocity must be faster than the outside wall. Okay or not? Alright? Wall velocity must be 0. In center the velocity must be faster than 0, if not nothing moves. Okay? It comes in at the same V in, V out. G and G. Okay? And they're all equal. Equal. Alright? V in equals to V out, G in equals G out. And now we have head. There's no turbine in this system. Head pump equals to 0. What are we left with? Alright, we are left with an equation looking like this. V squared, 0, 0. P in on rho G plus nothing is equal to P out on rho G plus head loss. Okay or not? Yes, that one gone. Okay, so the velocity gone. Mg head what G? G obviously is the same. The head is the same. Sorry, head in and head out the same. Straight length of pipe. We are left like this. All right, and in this particular case, KL equals to 0. No minor accessories. Alright. So we can say the head loss is actually 64 on RE. No, that one comes to F L on D, V squared on 2G, P in on P in minus P out on rho G is equal to this one. Alright? Because no minor losses also. So the equation up there simplifies to this one. Let's try to work out what F is for laminar case. Okay. Any questions? Major losses, this is major losses due to pipe. Minor losses, accessory. All the other elbows, bends, valves, and so on. Right? Major losses, this is the major losses due to pipe. Alright? Due to friction in the pipe. Right? Okay. So there are a few ways to work out this F. Alright. Alright, there are a few ways to work out this F. This B here. Now you ask what's the problem. because the V varies from 0 to some maximum. Alright? So, here is the maximum. Here, the velocity V equals to 0. Okay? Okay? So, this V normally is based on the mean velocity. Okay? The mean velocity, V mean, how the definition of mean velocity is m dot equals to rho A V mean. Alright, it's based on mean velocity. Okay? Right, then how now? Okay. Okay. So now we need to sidestep a little bit and look at laminar flow before we can come back to this equation. Alright, so don't forget this one. We'll come back to you. We'll come back. We'll be back. Okay. We'll come back to you. Don't make sure it doesn't run away. For laminar flow, all right. Again, I said far away. All right, it has that velocity profile. All right. If I drew a control, okay, so this is the center line. I drew another control volume, say in green. This distance between here and the center line, distance R. Okay? Let's do it the simple way. Let's just, okay, so R is the arbitrary distance from 0 to VR. R is the radius of the pipe. Here, this distance, R equals to big R. Okay? So let's do a analysis on that, this thing here. Okay, so this distance here is L, length of the pipe. Alright. Here normally is P1 or P in. Here is P out. Alright. We assume and it is correct that the pressure gradient, there's a constant pressure gradient now. Alright. But actually you don't, it'll come out later lah, but actually the dp, if this is a distance x, right, dp on dx is equal to p out minus p in over L. And you expect something less than 0, isn't it? Because the pressure on the outside, pressure out will be less than in. Okay? So this will be less than this. You take this one minus this one, you'll get a value less than 0. So we expect a negative pressure gradient. Okay? The velocity also, okay, the velocity, well, the du over dr, we expect less than 0. Okay? Because from the distance, as you go out, the velocity is slowing down. As r increases, the velocity is decreasing. Okay, no? Right? We assume some profile. We'll work out what the profile is. But definitely it's a negative profile. Okay. So with that in mind, so let's hope we don't get too confused. Alright. Some of the forces on the green control volume must equal to 0, right? Steady state and fully developed. Okay? So the profile is already fixed. At some stage it will be fully developed. The profile not going to change anymore. Far away from the entry, far away from the elbows or whatever. Right? So the profile is fixed. No, it's fully developed, right? Which is very straight. Later we will talk about when it's not fully developed, but for now, let's talk about fully developed first. Okay? So this is equal to P in times pi r squared minus P out times pi r squared. Now it depends how you draw the shear stress. Shear stress. Alright? So, actually I know already the shear stress is going the other way. But I draw it. You have to be careful of your sign direction, you want to get messed up. Alright? But there is shear stress on the, so that green thing is like a sausage. Alright? A sausage that is smaller than the pipe. Okay, the pipe diameter or pipe radius r, the green thing is diameter small r, which varies from 0 to big R. So it's this is the, I'm doing it on a small pipe. Alright? Hopefully I get it out. Okay, so fully developed. Then it depends whether you put plus or minus. So I put plus if you're doing it this way. Okay, that's the positive direction. Okay, shear stress multiplied by area. What's the area? What's the area of the outer skin of the sausage? Pi r will give you the circumference times L. Alright, not? Pi r is the length. Oh, so 2 pi r L. Okay, put 2 there. Let's work in terms of r first. I don't d and all that. 2 pi r times L. Alright, and that is equal to 0. So, shear stress can cancel out the pi lah. What's the point carry so many pi? Alright? In fact, can cancel out 1 r also. Okay, cancel out 1 r lah. Alright? So, we have shear stress times L is equal to P out minus P in over L. There's R here. P out minus P in. Alright. So this is actually dP dx is equal to dP over dx multiplied by R. Alright. All still follow no? I pull any tricks here. Okay, now the trick will come. Shear stress is equal to mu du dy. On this case, this one, mu du over dr times L. Okay, no more. What's the go there? L. No, the L no more here already. Is equal to dP on dx multiplied by R. Is that correct? Yes. Du over dr is the velocity gradient. Right? Du over dr. This is by definition, this is what mu is. So du dr is the velocity gradient here. Alright, as you go R here, this gradient here. The rate of change of U as you progress in R, this gradient here. This one is the U, this one is the R. So you can see the gradient is negative for you. Is that alright? Oh, I forgot to tell you also. We are assuming that the pipe is long relative to the system, so the pressure across the face is uniform. In other words, P in, the whole side face is P in. P out, the whole face is P out. We assume there's no variation in pressure across at any one point. In other words, if say P in this from here all the way to here, that's P, the same pressure. Is that okay? That's one assumption I forgot to tell you just now. That's okay if you have a long pipe lah. Alright? This pipe is, the L is much big, L is typically a lot bigger than P. Alright? It's a lot. Alright? So the pressure variation here is going to be very minimal compared to the pressure variation here. Alright? Okay? So from here, so you can see here also, one, U is only a function of R, P is only a function of X. They are two independent things. Alright? P varies with X, U varies with R. U doesn't vary with X because fully divided. Okay? Let's see whether you can put in something. Alright? So du over dr is equal to, I leave it in this compact form, but later I can expand it back out to this one. These are the same. P dp dx or P out minus P in over L. Du dr equals to R over mu dp on dx. U oh, lost the 2 2 here, so the 2 should be here, so the 2 should be here, so the 2 should be here, 2 should be here. Okay. U is integral R over 2 mu dp on dx dr. Okay, not? U integrate this over here. U dr. This is only a function of x dp dx. So as far as R is concerned, it's a constant here. Actually, all the constant you can take outside. Okay. So hopefully I don't mess it up. 1 over 2 mu dp on dx. This one, u is actually r squared over 2 plus c. Okay. All right. What is C? Yeah. When R is 0, boundary condition. When R is big R, U equals to 0. So we can say 0 equals to 1 on 2 mu dp on dx R squared on 2 plus C. So C is equal to minus R squared on 2. Multiply by all that feature. Multiply by 1 over 2 mu dp on dx. So actually the velocity profile U is equal to, as a function of R, is equal to 1 over 2 mu dp on dx. Huh? Oh yeah, because if I leave c inside here then there's no need multiply. All right, c can be inside or outside it's constant because I left c inside here, multiply by this constant, or I can took c outside. Okay, so this time I left the c inside, so c inside, then there's no need to multiply. This mu can 2 mu multiply by 0, dp dx can also go and multiply itself by 0, it will not. Okay, okay, so r squared, why the 2, put the 2 outside 2 outside, get 4. R squared minus r squared. Right? This shows you that the velocity profile is parabolic. Right? Parabola. This one is a constant. Alright? This one okay. You might say, hey, hang on. When r is 0, we have the velocity profile, the velocity at the center line equals to minus r squared as this thing. But that's okay, because this is also negative. This negative will cancel out this negative. Alright? So the velocity will be positive. It's going to be over in the positive direction. Alright? So when r is 0, the velocity is actually, so you can expect the maximum velocity at the center line. U max is when r equals to 0 is equal to what? Minus r squared on 4 mu dp on dx. Okay, that's the velocity profile. Okay, now we want in terms of the mean velocity, because we've got the velocity profile as a function of dp dx. We've got the maximum velocity as a function of dp dx. We want the mean velocity as a function of dp dx. So u mean times area is equal to u dA. I want rho. Okay, that's the definition of mean velocity. Rho mean times area, m dot, and this is the rho dA. Okay, m dot. But before I embark on that one, you're all happy with this? I didn't pull any rabbits out, anything you're not like make you upset or thing like that? Okay, I'm going at the adequate pace and right, and I didn't pull a fast one or side of hand or thing like that. All right. Okay. Because why we need mean velocity? Because this f just now way up here we told you I'll come back. All right, where I come back here. All right, this f is in terms of mean velocity. All right, we want pressure drop in terms of mean velocity. So let's see. Okay, I think the this rho can cancel out. U mean times area is pi r squared. That's area equals u. U is 1 over 4 mu dp over dx r squared minus r squared. dA is actually what I told you dA was? Pi integral dA, oh there was integral here. dA is actually 2 pi r dr. Alright, for those who forgot, and R equals to 0 to big R. Alright, it's the pipe area, pipe is a circle. Alright, dA, which is this one, is equal to 2 pi R dr. dr is this distance here. Alright, so dA, the area of that little ring, alright, is equal to the length of that little ring, 2 pi R, times the thickness dr. Okay, so now we got some challenge here. Now okay, looks quite easy. Right? Now we're challenge here. So let's integrate and see what the mean velocity is. Okay? Times. Sorry, this is big R. Huh? Sorry, this area is pi R squared times pi R squared is equal to, bring out all the constants. Alright, 2 pi over 4 mu dp on dx. This r squared becomes r cubed over 3. This r squared becomes minus r squared. Is that correct? 2 pi 4 mu dp dx. Hang on. This r cubed, integrate r4 over 4. This r times r squared becomes minus r squared over 2. And we integrate from big R to 0. Okay. Alright. The 2 pi, the 1 over 4 mu dp dx, all put outside. Left inside r squared minus r squared, but there's an r there, I multiply. So r cubed integrate becomes r to the 4 over 4. R integrate becomes r squared over 2. Okay, so far? Alright, so if you put that in, you got u mean times pi. Actually, pi can go away lah. R squared, pi and pi can go away, equals 1 over 2 mu dp over dx. R squared, r to the 4, this one, minus r to the 4 on 4. 0, 0, nothing lah. R to the 4, r basically is r to the 4 on 4 minus r to the 4 on 2. Quarter minus half, you get minus half, minus quarter. Alright? So, and after that, you can cancel this one and this one cancel. 2 u mean is equal to 1 over 8 mu dp on dx. 4 times 2, 8 r squared. Okay. All right. Still negative one. It's still negative here. Okay. Why? You might say why negative? Because this negative must cancel out. dp dx is negative. Pressure drops up as a function of x. Right? So as x increases, pressure drops, is negative, and so you get a positive velocity, even though even though there's a negative sign here. So don't panic. We're okay. Alright? So all this part here, don't think you say, oh, don't need to know. Sometimes those fellow, they'll test you this one. Okay? You have to know a little bit. Cannot have nothing inside. Just all robot only. What do we have to do now? Okay. If we don't like the diameter radius, we can put diameter minus d squared 2 square is 4. 4 times 8 is 32. Okay. Alright. How we go from 8 to 32? Because dr is d over 2. So, r is d over 2. So I replace r with d over 2. So I get d squared over 4. 4 times 8, 32. Alright? Okay. So now, find f. Or dp on dx is equal to 32 mu u mean over d squared. It's a minus. Okay? Alright. What we need to find, now what we need to do is rearrange this so we look something like this. Hopefully. So we can find f. So copy. So just as a guide, I place here. Alright, so I know where I'm going. Okay. Right, I want in this form so I can find f. Okay, so let's see. What if okay, you got a u mean there? Okay, all right. So what if this one is actually p out minus p in over L. Okay, you're assuming the gradient is linear, which it is. All right, is equal to minus 32 mu over d squared u mean. Okay, so can I say here is p in minus p out? All right, so p in minus p out over L, we can drop the negative, 32 mu over d squared u mean. Okay, I want the L over there. So multiply that, bring the L over there. Okay. Bring the L over there. Actually, before I go on, this one is a big equation. I got name for this equation one, I think. We call the Poiseuille equation or something. Alright? But that might lah. You can read the textbook for all the history and the names. Alright, but that one actually that one is a right, you already found the mean. If you know the mean velocity and the diameter, you can predict the pressure drop from here, this equation. Alright, this is actually an important equation. Alright, this is an important equation, and also this one is an important equation. Poiseuille or something like that. I can't remember. There are a few names. And this one is also an important equation because this is the velocity profile. Alright. So don't just put in the filing cabinet somewhere. No, these are important milestones along the way. Yes, but the dp dx is actually constant. Alright? It's not a parabolic or thing. It's a, yeah. Huh? In a fully developed flow, it is constant. It's just a constant pressure drop. Alright? Not it must be constant because let's say this 5 meter of pipe, the pressure drop is a certain number, then the next 5 meter pipe, the pressure drop must be the same one. Okay, now here this 5 meter pressure drop something, then the next 5 meter pressure drop something else. But the velocity profile all the same. It doesn't make sense. Yeah. Okay, so dp dx must be a constant. Alright? Okay? So okay, so if I divide by, I move the L the other side, so I do slowly step by step, so you don't feel cheated now. $32
L mu over D squared U mean. Okay. Next step, I want my equation to look like this. Okay. So, because this is the definition of friction factor. Oh, I forgot to tell you the name. This is called friction factor. Alright? I got name. Okay? So, what is it? Okay? So, P in minus P out over rho G. Okay, now I have to divide both sides with rho G, right? Okay, equals to 32 L mu over rho G D squared U mean. Okay? Now I want to group it together nicely. How? Okay, so this is equal to $32. Actually, I put 64 lah, because there's a half here. Okay, not 64 times half 32. Right not? Okay. There's a L on D, and there's a D here also. So this L is here, this D here and here. No tricks yet, huh? Okay, I covered 32 L D. Well, how do those do? Let's see. So L on D. And a half. So far, okay, I got the 32, I got the L. L on D, V squared. Half L on D, half. So you mean square. Okay, 64. The mu is still here, mu here. Why I put square? Because I put the u mean here also. Alright. Okay, the rho I put here. L on D. Oh, the G. Half V. So actually this one, don't put half lah. Put u mean u mean squared over 2G. Okay now. So everything is there. 32 is 64. Divided by 2 is 32. L is there. Mu is comes here. Rho is here. D and D, take your D squared. The G went there. The u mean, here u mean, and here u mean. Squared and here rho. Right? So everything is there. So if some of you are sharp, you realize this is already rho V D over mu is your Reynolds number. Okay? So it's equal to 64 over RE, L over D, U mean squared over 2G. P in minus P out over rho G. So this equation looks exactly the same like that. Alright? Hopefully you believe me, you didn't I didn't pull anything. Alright? Everything is accounted for. I didn't create anything, I didn't disappear, like hide anything. Alright? Okay? So for laminar flow, that is your F. Okay. Alright. L and D. So for laminar flow, that's your F.
where RE is the same for all flow, for all pipe flow lah. RE is normally rho V D over mu, where this V is the mean velocity. Okay? Not bad, huh? Can do this one. Right? I do it my way also. My way, okay? You don't like my way, the textbook got their own way, the lecture notes got their own way. Right? Maybe on the internet, Wikipedia got their own way. Right? And lots of other way, right? Also okay. Okay? But it all comes down to 64 RE. Right? If it doesn't get to 64 RE, then maybe that way is got problem. All right. So, any questions so far? Huh? You might. I cannot guarantee you won't. Looking at the trend of past year questions, you better know a little bit. Okay? Know how it came about. This is useful here, and the non-Newtonian pipe flow one also, they tend to ask this one. Okay, now come some story lah. Alright. So the story it goes, alright, that just now I assume that the flow is fully developed. Okay? In other words, the profile is not, the velocity profile is not changing anymore. Alright, we have a constant pressure drop for the unit length. Alright, dp dx is constant. And how that comes about is, okay, look at this picture. No, very nice small picture, like same picture as that. Alright, you have a tank. Let's say, for example, a tank with the flow entering the pipe. Alright, so actually, this picture not nice lah. Not that I can draw better lah, but I. Alright, normally they draw like this one lah, like a trumpet. Okay, this is a smooth entry to a pipe. Okay, so when it comes to at the inlet, the pipe, the velocity uniform. Okay or not? Same like the boundary layer growing on the plate. Yeah, I hope you remember that story. So not very good. The pipe is not converting into everything. Okay. So it comes in, and when it enters the pipe, the velocity profile initially, so at some point the boundary layer grows up. Here the boundary layer very hard to grow because, but at some point the boundary layer grow. Is that alright? So in other words, initially no boundary layer means like this, okay? No bound, and here there's a thin boundary layer. Alright, let's say here there's a thin boundary layer, followed by uniform flow, followed by thin boundary layer. Okay? No good. Picture no good. Try again. Don't worry, it's the same picture if you try to draw. Hopefully you draw better than mine. Okay? So the boundary layer grows. Alright? Here. So here, before the boundary layer grows, the velocity here is uniform. Alright, it hasn't touched the pipe so much yet. Here, the boundary layer is grown like this and like this. So here is the velocity still uniform, and this is the boundary layer. Okay or not? Alright, the boundary layer growing in the pipe wall. Alright, but the pipe is circular. So I need top and bottom, but there's not top and bottom pipe wall. The pipe wall is also all around. Okay? There's wall in front of you, there's wall behind you. Alright? So, and the boundary layer is growing. Alright? Up to a point, the boundary layer can't grow anymore. Because the boundary layers will all touch each other. Right now. Okay? So, at that point, where the boundary layer grow and until it cannot grow anymore, then what happens to the velocity profile? Okay, then obviously there's no part where the velocity profile is really flat anymore. Here the velocity profile is that parabolic profile. Okay, and continue on. So this is fully developed. Okay, that's why we prove our thing just now in the fully developed region. And that's how you get to the fully developed. You allow the boundary layers to grow and grow and grow until they all touch each other, cannot grow anymore, and then they continue on. Obviously, the velocity profile cannot evolve anymore because the boundary layers are here. Alright? So here, I told those that attended the tutorial of Wednesday. Here the boundary layer is thin. There the boundary layer is fatter. Already touched. The fatters you don't get already, right? The boundary layer is essentially all meet together in the middle of the pipe already. Alright? And onwards, the velocity profile is constant. It doesn't evolve anymore. Alright? So here the boundary layer is thinner than that. Okay now? Alright? So fully developed does not evolve. Does not evolve EVOLVE with X. Right? Does not evolve. Maybe I don't try and change evolve. Does not change with X. Let's not use too powerful word here. Alright? Okay. What was I saying now? Okay. So it does not evolve with X. I forgot something. Alright? Okay. So I told the group earlier already. Okay, so you expect that the boundary layer, the factors, does not evolve with X, so you get a constant, you keep the X really constant. Alright? So the pressure drop is really due to, well, we looked earlier. Way back. If you feel the pressure drop is due to, I forgot where it is. The pressure drop is really due to this shear stress. Alright, no? Okay, the shear stress at the wall or the shear stress internally is the same. Alright, and really, so here the PT is constant. Alright, so here the pressure drop is due to shear stress, and the shear stress here is higher or lower than that. Alright, is equal to mu du over dy. Do you expect du dy to be higher or lower than that? Alright, so while I draw, you can see du dy here. Look at the gradient here. Steep, right? Okay, that's steep, right? Okay, when you have steep gradient, when you have fast moving fluid, thin boundary layer, okay, du dy high because depends. I give a different explanation depending which one you accept, which one you buy. Fast moving fluid near wall, or you want thin boundary layer. If you have a thin boundary layer, all right, between the boundary layer, all right, between the wall and the top of the boundary layer, the velocity has to go from 0 to full speed. If you have a thin boundary layer, then your change in velocity has to be fast, because thinner, just go from 0 to u in a very small distance. If you have a thick boundary layer, then you can gradually grow. All right now. So if you have a thin boundary layer, or in this case, you can see you have closer to the wall, you have fast moving fluid compared to there. So you expect high du dy, therefore you expect higher shear stress, therefore you expect the P pressure drop is higher. Okay? So for entry length, before the velocity is fully developed, you can expect the pressure drop to be higher than the one we estimated. Alright? Is that okay? So pressure drop expect to be higher at regions where the velocity is higher. Or at the entry region here. Alright? Normally, we don't worry too much about entry region in this unit. All right, but it's part of the thing, so I have to talk about it. Normally, all right, but and I can't guarantee it will not come out in the exam. Although past 10 years, I don't think it has. But they might give you a surprise. All right, but in this unit, many will worry about very long pipes. The entry region is a very short portion of it. But if you are in your practice or whatever you do, you are working with very short pipes, then you need to consider that your pressure drop might be higher than that predicted. All right. So an entry region, this slide here. Do look at this, because I'm not going to write everything from it. All right. These numbers also in your textbook. All right. Entry region, not only the region where it enters, but if the flow goes through some accessory or some bend or something, then the flow not quite steady yet. Okay. Then it takes a while to recover. That also can call like an entry region. Okay. So it's like the flow goes through a bend, elbow. So the flow is a bit, the boundary layers are all a bit out of adjustment. Okay, because of the some pipe going faster than the other and so on. Go around again. Alright. So it takes a while to adjust. That's also called a boundary development length. You can expect that short region after the elbow, that the pressure drop is higher. Alright. If you ever need these two numbers, don't need to memorize, but it's in your textbook. Alright. For turbulent laminar flow, the entry region is actually quite long. L over D equals 4.4 R into 1 over 6. Alright. So for Reynolds number like 200, the length of the diameter you might take 200 or 300 diameters or something really long. Alright. But for turbulent flow, the entry line is a lot shorter. L over D equals 1.06 for turbulent flow. Okay. So these are experimentally determined. Alright. Safe. Okay, so what else? The remainder of the time I have for today, the plan is to talk about the transition to turbulence. That one's important. Definitely important for me. Transition to turbulence and how you estimate turbulent pressure drop or turbulent flow. That one very important. Okay, you don't have to wake up. Okay, so this experiment, there's a famous experiment done by, that's why this Reynolds number called Reynolds, but obviously he didn't call it Reynolds number. Nobody's ego that big. Alright? So it was called Reynolds number only after him, right? But there's a famous engineer, mathematician in University of Manchester who did this experiment. Alright, it's a pipe flow experiment. Can't be repeated now because although if you even use the same rig, because the outside has all changed, there's a lot more disturbances. Alright, there's a big road in front of the antenna and all that. So things, but when he did it in the 18th century, he found, alright, that for the flow below a certain, whatever dimensional parameters used then, now it's called the Reynolds number, alright, the flow is laminar. Alright, so here, same argument, the viscous forces dominate. Alright, any disturbances get damped out because it's viscous. It's like glue, it's like you falling into quicksand very viscous, you cannot move. Alright, so it tends to damp you out and eventually you die. Okay, so eventually any disturbances die. Alright, there is a number experimentally determined, but this number can vary depending how steady you are. Alright, how stable your experiment is. Whether you are in a place, some places, if you are in the top building, you don't got shaking and all that. Even the slightest of shake can move this number. This is very sensitive. If you are operating at around number few thousand, experiments are very sensitive. Alright, but for this unit, they call this region the transition for our analysis purposes. But the number can be moved down or can move up if you are a bit more steady. Alright, to be up to 10,000 or whatever, you can still get enough flow if you have very steady hands. Make the pipe very smooth, make your system very stable, no pump, but minimal pump vibration and so on, those kind of things. Alright? Maybe you slow down your heartbeat so that you don't disturb the breathing. Maybe you don't be there also. Right? Okay? Then you can push it up. It can go up. Alright? I'm just telling you. Alright? But for these numbers are typical, alright? At 2100 below is laminar flow, 4 hour laminate like laminar board, laminated. Right?
here you have transition. Transition is when you have this part here is a little bit of this and a little bit of that. Okay. Sometimes you get spots of turbulence, then after it dies down and spots of turbulence and die away and so on. Right? When turbulent flow, again it's turbulent. There's a lot of what do you call that? A lot of disturbances, and the disturbances can sustain. Alright? So if I were to draw the profile, okay. If I were to draw the profile, okay, this is laminar flow. Alright? If the turbulent flow, alright, okay, obviously turbulent, the velocity must be higher, so, but if it was turbulent flow, okay, there are a lot of these eddies going this way, some small, some big. Obviously, it cannot be bigger than the pipe. Right? Okay, the maximum size is the pipe diameter. Minimum size is until the dissipation kicks in. Alright, they are not all going only this way, some are going into out of the page and so on. Alright, so all that mixing causes the things to profile to look like this. Okay? Alright, so you expect here relatively the du over dr here to be low, here to be high. Is that okay? Because of the where I exaggerate that. Okay, here to be high. Is that alright? Because of the mixing of the fluid, most of the pipe velocity is uniform except very thin boundary layers. Here you get very thick by the boundary layer. Okay, right? It's very thin, very thin. Right? If you go up to Reynolds number, hundreds of thousands, million millimeters or micrometers. Okay? This is du dr, that's fine. So you expect here the shear stress to be low and the shear stress to be high. Therefore, you expect the dp on dx to be low and the okay? So you expect more pressure drop for turbulent flow. Alright? But most flows are turbulent. Because to build pipes, just to do laminar flow, the pipe should be very big, and then you waste a lot of material and a lot of volume and so on. So compromise is where turbulent flow, but you be more generous to the pipes, I think. But the flows will generally be turbulent. Okay. Any questions so far? Alright. So with this one, turbulent flow, that one that no analytical results. Okay, so there's no proving all sorts going around and around and all that. But there is experimental results which they have summarized nicely for you. All right. So there's an equation I think it's called the what equation, but we never use it. All right. I can't remember the name also. We never use that. There's an equation, but what we normally use is this chart. So I better teach you this chart. Where's the Moody chart? Here. So small, yeah. Can see, yeah. Maybe a bit better here. Okay. So the Moody chart, all right, is basically a compilation of all the turbulent results nicely compiled for you, so you can use. All right. Only thing is, so this is the friction factor F. The above there is the Reynolds number. All right. And here is the wall roughness. For laminar flow, that below 2000, just now we showed, the F is 64 over RE. Alright? No problem there. Okay? F, no problem there. But, and it doesn't depend on any other thing, it just depends on pipe. Because the boundary layer very fat. But for turbulent case, it depends on the roughness of the pipe. Because the turbulent the boundary layer is very thin. Alright? So it interacts with the boundary layer, with the wall of the pipe. So it does depend on the pipe walls. Right? So this is the relative roughness. So each relative roughness is the roughness over D. So each material typically has a roughness value. That roughness value, sometimes you can look it up in the textbook to estimate it. Sometimes the manufacturer will tell you. Sometimes the manufacturer will lie to you, but you know, that's life. All right, so that one. For this unit, normally we tell you like that. Or we can say it's a smooth pipe. Right, the bottom there. Okay. Got any numbers? All right. See whether his lecture notes got any numbers. Ah, got here. A bit small only lah. So these are some typical values for the roughness. You also pull out the textbook up. Okay? So typical roughness, either in feet or mm. It's pretty small. Right? Smooth 0. Typical roughness. Cast iron, the pipe's a bit rough on the inside. There. Concrete and so on. Concrete, yeah, worry about water leaking out. Concrete porous. Okay, you must do some treatment for that. Okay. Okay, what else do we have? What am I supposed to have? Oh, just a few notes on this one. Okay, number one. See, after a certain Reynolds number, for depend on the roughness, after a certain Reynolds number, the Reynolds number doesn't have effect anymore. It just purely depends on the roughness. Right? It's nice to straight. Alright? So this is the wholly, what is it? Complete turbulence. Complete turbulence. Alright? Completely turbulent. What it means here is that as you increase the Reynolds number, that boundary layer is getting thinner. It's getting thinner and thinner and thinner until it's so thin that any further thinning of the boundary layer has no effect. In other words, basically your, what do you call it? Your mean free stream flow is already interacting with the roughness of the wall. And therefore, the increasing the Reynolds number doesn't change the friction factor. That's what it means in this region here. Okay? In this region here, there's that effect of the relative roughness and the wall, the boundary layer. Okay? Number one. Number two, here all can read the numbers. No problem. 0.01, 0.02, 0.03, 0.45, and so on. 2, 3, 4, 5. You can see it's logarithmic scale. Alright? That's why from 0.01 to 0.011 is a big scale. Okay. Right? But for 0.019 to 0.02 is a small one. Okay now? Alright, so be careful, this one logarithmic. And also here logarithmic. Here is blah blah, I can't see, can you see now? Yeah? Can you see now? Alright? You know, you look at your book, I think here is 10 to the 1. 10 to the 3. Here 10 to the 3. 2 by 10 to the 3, 3, 4, 5, 6, 8 gets smaller, up to get 1,000. 10,000, 20,000, 30,000, 40,000, small. Here is 90,000, 100,000. So from 100,000 to 200,000 is a big gap, and goes small because logarithmic scale, so that you can show the data from 10 to the 3 is what? 1,000 all the way to 10 to the 8. 100 million. 100 million. Okay? From 1,000 all the way to 100 million. Alright. So, any questions so far? Alright, so let's do something important now. Alright, let's do an example. Alright. Okay? Let's do an example, and after the example we can go. And after tomorrow's tutorial, we'll go.
catch up on sleep or whatever other things you catch up on. Studies. Okay. Alright, let's say, so no, right now we don't know how to calculate minor losses. That one we'll do later. So let's say pipe. Okay. Let's say the municipal type water pipe. How big it is? Maybe diameter 100 mm. All right. Calculate. So the water rho is 998. Mu is what? 1.2 times 10 to the minus 3. Is it? Correct. Okay, 100 mm pipe, so it's quite a big pipe. Alright, maybe it's not like a neighborhood pipe. Not the pipe to go to your house, the pipe to your house maybe 50 mm. Huh? Not 10 cm. That one, the pipe coming into the one single tap, maybe 25. Alright? Let's say what's the pipe made of? Galvanized iron. Alright, normally called GI, galvanized iron pipe. Velocity. Let's do length. Right, typical distance from there maybe, I don't know, 600 meters. Okay, calculate power loss. Let's do two cases. Case 1, we do laminar at RE 2000. Right, we need to find the velocity. Find V. Case 2, that's the velocity be what's 30, 20, 10, 15, 10, let's say 13 meters per second. Okay, I'm sure that's turbulent. Alright, so I'm sure the case 2 is turbulent. So let's say the Reynolds number 2000, very small Reynolds number. Find HL, alright, delta P, and power loss. Okay? For this one, for the first case, find V also. Okay. Alright. So you okay with the problem? Safe. All right, the problem. You can strongly recommended to follow along and do it so that you don't fall asleep. Okay. Just the faster we do it, the faster you go home. Alright. Find V. What is V? Okay, so case 1, RE is equal to rho VD over mu. It's equal to rho 1998 V diameter 0.1 over mu 1.2 by 10 to the minus 3. That's correct, isn't it? That's the best I can remember, more or less. Equals to Reynolds number 2000. What is the velocity? Huh? 0.02 meters per second. So for such a big pipe, the velocity is to keep it laminar flow, the velocity is very low. Very dripping away. Alright. Alright, so fast, huh? Like a snail. Alright. What do you need, huh? P. Alright. I write the full equation. Alright. P in over rho G plus V squared over 2G plus H plus head turbine is equal to P over rho G plus if I jump this one after you cannot follow. Let me say H loss plus head pump turbine. So this pump here. Alright, for this case it's just a straight piece of pipe. So the H pump don't have, no turbine. Head loss is F L on D V squared on 2G plus sum of KL V squared on 2G. This one also don't have. Alright, that one definitely have, can cancel out. Straight pipe, we assume fully developed at the inlet and outlet, so the velocity is the same. And it's horizontal pipe, so the height is the same. Okay or not? You all follow my argument so far? It's exactly same like what just now the problem we did now. We start with the kindergarten level stuff. So it's just a straight pipe. Later on the pipe got bend, got twist, expand, contract, go through pump, go through from tank, one tank here, tank up the hill, tank down the hill. Alright? And then you have to do it. Alright? That's an exam question if you have. Right? Won't be straight pipe. That can guarantee. Right? Okay. So here we have P then I got the out. Pump put work in, out, alright. Okay, correct. P in minus P out over rho G is equal to F L on D V squared on 2G. Alright? And this is basically a head loss. Alright? Which is equal to HL. Alright, here, so the first case, laminar flow. So F is 64 on RE, 64 on 2000. Length is how long? 600 meters. Diameter 0.1. Velocity 0.02 squared over 2 times 9.81. Alright, equals to head loss. So please calculate head loss first before we calculate the pressure drop. What's the head loss? And that answer will be in meters. .039 meters. So the power loss, if you are keen to know what the power loss is, m dot GH loss equals to m dot is what? Rho 998 area by 0.1 squared over 4. Rho AV velocity 0.02. That's m dot times 9.81 times 0.039. That's what, huh? Right? M dot, yeah, sorry, I just a side calculation. Rho area velocity multiplied by G multiplied by M. What's that? And someone else calculate the P in minus P out is how many Pascal? Rho is 998 also. So what is it? So that's for the laminar case. That's how you calculate it. 381. 381. Power loss 0.06 watts. Okay. All right. Okay. Now turbulent flow. Okay. Turbulent. Well, I expect it to turbulent. Let's calculate. Let's double confirm. Case 2. Rho VD over mu 998. Velocity is 13. Diameter is 0.1. Mu is 1.2 by 10 to the minus 3. What is it? Alright. And here I said it's galvanized iron pipe. So say this first. Sorry, I flip over to other page because I don't know what the roughness is. I did it up here. Galvanized iron pipe, the roughness is about 0.15 mm. So E is 0.015 mm. Was that right? Okay. So here, 0.15, not 0.015. This number here. Okay. 0.15. E over D is 0.15. What's the diameter? 0.1. Close. 0.15 mm times 10 to the minus 3 over 0.1 meter. Alright. What's the Reynolds number? Huh? 1.08 times 10 to the 6. E over D? 15 mm over 100 mm. 0.15 mm over 100 mm. Times 10 to the? Alright, which is 0.0015. Okay? What is what? D is 0.1. This is the roughness of the pipe. So I said in the question, I said galvanized pipe. Then I looked up the table, galvanized pipe. The textbook told me it's about 0.15 mm, the roughness. Typical for galvanized pipe. It could be different. I told you that number. Textbook got some values. Manufacturers got some values, and so. All right. Okay. So step 2, look up F. Look up F. Can you look up F? You all ready for that? Alright, let you finish copying first. Any questions? All happy? All happy? Alright, so we look up 1 million, 1.08 million, and 0.0015. Let's see. Okay, 0.0015. 001. Somewhere around here. Okay, here's 0.001, here 0.002. So our relative roughness is about between this line and this line. Alright, say halfway lah. Okay? Reynolds number 1 million, 10 to the 6 is about here. Here's 2 by 10 to the 6. Here's 2 million, so our 1.1 is very small here like that. Okay, so we go up. Alright, so we are between here, this line and this line. This line is 0.002, here is 0.001. So estimate halfway lah. Alright, and then go out that way. Maybe here. 0.021, more or less. No, wrong.
2 lah. Okay?
Alright, say 202122 is here. 0.022. Okay or not? 022, 023, never mind lah. But exam I won't be so, as long as you're more or less reading the graph correctly, I give the answer. Right? What a lot of people tend to do, they don't look at the Reynolds number. They just take the relative roughness. They see here. My relative roughness 0.002, whatever, I just go straight. Okay, that happens not in the exam. Alright? Oh, that's a typical mistake. I don't need to look at roughness and go. Okay? No, you need to look at both. Alright? So if that's the case, come let's finish off. 0.0. What is it? 22. Alright? So put back into the same equation. Okay? Same except this is not 64 RE anymore. This is 0.022. Velocity is not this one anymore, it's 13 squared. Yep. And Pascal. P in minus P out. This one. What is it? Huh? Okay. You copy the up here, do you know? Alright? Okay, so I copy here. So, first step, find the head loss, and then power loss is equal to m dot GH. M dot is what? Rho 998 times area pi 0.1 squared over 4 rho G rho AV times 13 times G 9.81 times head loss. I don't know yet. What's the head loss? Huh? How many meters? Huh? What? 1. So high? 1137 meters. Yeah? You sure? F L on D, V squared on 2G. Alright. So, sure. Okay. So put it in 1137. So what's the pressure drop? 11.13 megapascal. So maybe 13 meters per second is too high. Typically, house water pressure from the mains typically around 400. Gauge pressure about 400 kPa to about, depending where you stay, 700 700 kPa. Okay, yeah, maybe 13 meters per second too fast for the pipe. 13 meters per second is very fast. Right. But we're moving a lot. What's the m dot? Just this part. How many kilogram per second? 102 kilograms per second. Okay. Alright, I made sure it's definitely turbulent. Okay, okay, so stop the record.